Hello friends, welcome to LogicHeap. In this tutorial, we are going to cover Introduction to Trees. Trees is a vast topic. We'll start with Tree ADT and then we'll narrow down our study to binary trees. Again, whenever we study any new data structure, we see how we can perform traversal, insertion and deletion. We'll cover each of these topics in a separate tutorial one by one. Till now, we covered arrays, linked list, stack, and queue, which are all linear data structures, meaning elements having one previous element and one next element if present. But data is not always linear, just like any family hierarchy. If you think about your family structure, it is generally like you can see over the screen. There's always a starting point you know of, which is called the root. It has got children, and then children of children, and so on. This is a non-linear data structure for sure, as a node can have multiple branches after it, not just a single element. Such data is best stored in tree data structure. Let's discuss some tree terminologies that we'll use very often. The topmost element, it is called root. Then let's suppose we have B. B is called child of A. B is child of A. And A for B is what? It is parent of B. A is parent of B. Same relation holds for all those nodes. Suppose if we talk about G, G is the child of C and C is the parent of G. So they hold the parent-child relationship between them. Nodes at the last which do not have any children, these are called leaf nodes. Let's discuss what is tree abstract data type. It will help us in understanding its conditions and operations that can be performed on it. Tree is a set of nodes that follows these following properties. First, a T can be empty as well, but if it is non-empty, it should have a special node which is called root. And root has got no parent. That's why it is called special, because it has got no parent. Second thing, every node apart from root has a unique parent node, and this very node is called child of your parent node. So only two condition, it has got a special node root, and second, they hold parent child relationship among each other. If we talk about the operations in tree ADT, these are the operations which must be implemented in tree. So when implementing, if you are creating a class tree, then created an object or an instance of class tree as T. Then T must be able to invoke all these methods, meaning in your class you should define all these methods. What are those? Firstly, T dot root. So it returns me the reference of tree. Second, if I pass second and third are around returning parent and children of node. So if I pass a node, I should get the reference of the parent node of it. And in the third method, if I pass the node, I should be able to get the iteration of all the children of this node. In the fourth method, if I pass the node, it should return true if it does not have any children, meaning it's a leaf node. And then in the fifth method, which is length of t, this gives the total number of nodes present in tree. And then how we insert a node is the sixth method. How we delete a node containing the particular value. How we traverse the complete tree node by node. And if we have a value, how we'll search that value in this tree. So these are all the operations that we need to implement. Now let's discuss application of tree data structure. Now, anywhere where you can see naturally a hierarchical data is coming in, you can apply tree data structure. One of the applications could be in the file system. So you have so many files and directories, and there's always a hierarchical relationship among them. So if you think in the Linux operating system, there's always a root slash, and then you see so many directories: boot, dev, etc, home, all these are directories. In these directories there could be further more directories or files inside it. So this is completely hierarchical data. Tree data structure is widely used in file system. In trees, we are narrowing our discussion to binary trees. What are binary trees? Binary means two. So every node has at most two children. It means it could have no children like the leaf nodes, or one child, or maximum at the most it can have two children, not more than that. Second point is, so every child node of the node is named as left child and right child. The one which is in the left is called left child, and one which is in the right is called right child. So if we have a binary tree, it is true that we only need to keep the reference to at most the left and right node. So if we think about implementing binary trees in memory, the node structure could be like this. If we consider this as a node, we can have three things in it. Firstly, your data itself. Let's say you have some data here. Then reference to the left node of it if present, and reference to the right node if present. So every node will have three things: reference to left node, data, and reference to right node. Now again you have its child. So this is called left child. Again it will have some data, let's say D1. Again it will contain reference to its children, and so on. So this is the structure of each node in the binary tree. So with the knowledge that we have gained, we can do a bare minimum implementation of binary trees. Since we have already covered linked list, it should not be very difficult for you to understand this. We have created two classes. First one is class node. So this is our class node. It has got three things: reference to the left child, reference to the right child, and data itself. And in the binary tree, we have one instance variable which is root initialized as none. So as soon as we write t assigns binary tree, it will invoke the constructor of binary tree. So it will create an instance variable as root, which is currently referencing to none. We have this root. In the next line, we are creating a node with the data as 10, and its reference we are keeping in the root instance variable. So now root is pointing to a node. This node has got data as 10, and in the left and right reference currently we have none. Now in the next line, if you see, t dot root dot left assigns node 20. So t dot root dot left is pointing to node 20. Then in t dot root dot right we have node 30. So let's create another node, and root dot right means this particular place, it is referencing this element. Now t dot root dot left. So this particular place, it contains the reference to node 40, and t dot root dot left dot right means this particular node, it contains the reference to 50, and t dot root dot right. So t dot root dot right is this particular element. It contains the reference to 60. So that's how we have created a binary tree here. So this is the minimal implementation of binary tree. Currently, we will not be able to traverse it, insert, delete, or search any particular element. In the next tutorial, we'll see how we can traverse a binary tree. You can check the link of code of binary tree implementation in description box.
Thank you so much, guys, for tuning into LogicHeap. If you like this video, please don't forget to like, share, and subscribe.